In this video, we will be talking about piezoresistive sensors. So what is a sensor? A sensor is a device that responds to an external stimulus or an input from the environment. The type of input signal can vary, such as from light, heat, and movement. Once an input signal has been received by the sensor converts it into an electrical output to be read and digitized. Pressure sensors are devices used to measure the force over a certain area. They can be used to measure the flow of a material, the force of two objects pressing against each other, atmospheric pressure, and in general anything that involves force. Piezoresistive sensor is a type of pressure sensor. When a mechanical force is acted upon the sensor, it changes the resistance of the sensor material, resulting in an electrical output. The magnitude of resistance change correlates directly with the amount of force acted upon it. The most common type of piezoresistor is the strain gauge. A strain gauge is made out of conductive material that deforms when pressure is applied to it. It can also be attached to a diaphragm that will change shape when pressure is applied. In response to the deformation, the strain gauge can change resistance in the system, which is then converted to an electrical output signal. Piezoresistive sensors are often used with a Wheatstone bridge to measure small resistance changes. This allows the sensor to be used to measure static and dynamic signals. The conductive material that a piezoresistive sensor is important to its function. The sensitivity of materials to resistance can be calculated through the gauge factor, which is defined as the relative change in resistance divided by the strain, or the relative change in length of the material. The gauge factor is often determined by manufacturers, so this formula is helpful in determining the amount of strain applied to the material given the resistance change output. There are two main types of materials that piezoresistors are made out of: metal-based sensors and semiconductors. Metal-based sensors are often made out of metal alloys. Some examples are nickel-chromium alloys, platinum alloys, and copper-nickel alloys. The resistivity of a metal, or how strongly a material resists electrical current, can be calculated by the following formula: the resistivity of the material, or the metal, multiplied by the length of the wire divided by the cross-sectional area of the wire. Based on this formula, we can see that the metal strain gauges change resistance due to variations in the material's geometry. Therefore, as the material length increases, the R increases as well. In contrast, as the cross-sectional area increases, the resistance decreases. Semiconductor strain gauges are made out of materials like germanium, single crystal silicon, and polycrystalline silicon. Rather than the geometry of the material causing a change in resistance, the change in resistance for semiconductors is caused by the redistribution of holes in the valence band due to the mechanical strain. During mechanical strain, the holes move from higher to lower energy levels, causing energy bands to deform. The mobility of the holes and the deformation of energy bands increases resistivity, which in turn increases the resistance across the sensor. Therefore, semiconductor strain gauges change resistance due to valence rearrangement. In general, metal strain gauges are more stable, while semiconductor gauges are more susceptible to environmental temperature changes. However, semiconductors have a higher sensitivity compared to metal strain gauges, which allows minute changes in resistance to be captured. An application of piezoresistors is in mammography. In a mammogram, the breast is placed on a machine that applies a certain amount of pressure from the top and bottom to allow for X-ray imaging in order to determine any tissue abnormalities. Strain gauges are placed on the pressure system to ensure that an appropriate amount of force is applied without pushing on the tissue excessively and preventing discomfort to the patient. At a certain force, the system will pause compression and allow for the imaging to complete. A big concept that people mix up is the difference between piezoresistive sensors versus piezoelectric sensors. To reiterate, piezoresistive sensors measure a change in resistance due to mechanical force. These are generally made with metal alloys or semiconductive materials and can be used for static and dynamic measurements. In contrast, piezoelectric sensors generate a voltage when a mechanical force is applied. These sensors are commonly made with ceramic and quartz and are often used for dynamic measurements since the signal decays quickly. There is much more information out there about piezoresistive and pressure sensors, but I hope this gave a small summary of how they work.